I'll give a quick background to why I'm here today. So I've actually been involved with RISC-V for about 3 years now. And as far as my industry experience goes, I initially started working in telecommunications a long, long time ago. And I moved into EDA back in 1989. And I've worked in EDA and semiconductors for 30 years. So I guess that makes me somewhat of a veteran. Woo! So you're probably thinking one or two things, which is, this guy's a veteran and he's really going to know his stuff, or you're thinking this guy's too old to be doing this stuff and he should have retired a long time ago. Now, we'll take a vote at the end. So this is what I'm going to go through. We're going to go through some information about verification of RISC cores, RISC-V cores, and I'll talk about what we mean by reference implementation, which is effectively what we do at Imperas. We build simulation models and simulation infrastructure in order to produce instruction-accurate models for high-performance execution. And then I'll go through some stages of verification. I'm involved in the compliance working group, so I'm going to touch a little bit on compliance testing. I'm also going to talk about directed testing, some work we've been doing with Google on the constrained random testing, and I'll try and bring into this what the goals of these testing methodologies are in terms of the architecture that you're trying to test and the microarchitecture that you're trying to test, because different types of testing address both architecture and microarchitecture differently. Okay, let's start with what a reference implementation is. So the first question I would ask is, why do I need a reference as part of my verification? So the purpose of having a reference as part of your verification is that you're able to generate a reference comparison of the behavior of the device that you're building. And what we do is we build a reference model which provides the entire ISA envelope behavior. Now, most implementations of your RISC-V device will be a selection of options from the specification. Now, the specification is pretty big. So if I was to say how many people have actually read either the user mode specification or the privilege mode, how many people have read it? Wow, I'm impressed. Actually, that's quite good. It's a pretty detailed and long description, and actually it has lots of alternatives that you can choose to implement, not only things such as the extensions, but also the options for behavior. So does your hardware implement misaligned loads and stores, or does it rely upon a trap handler to resolve those misaligned loads and stores? And there are lots of options in here. We've been involved in a number of projects using RISC-V, and that's both good and bad, to be honest, because the good thing is that it's RISC-V, the bad thing is that it's RISC-V, because RISC-V has so many possible alternatives. And if we just look at some of these, you look at the fact that you've got variations on the XLen, SLen, VLen, ELen for vectors, you have bit manipulation, you have custom extensions, you have different modes of operation, machine mode, user mode, supervisor mode, and the models that we build have to be able to address that, right? So this is the problem. It's a highly configurable architecture, and it can get a little complicated. Now, when you try to configure all of the components in your verification flow, not only our reference model, but also the compliance suite and things like the RISC-V DV flow, then you need to be able to provide a definition that constrain those to behave in a certain way. And one of the things we came up with help from guys in the formal group, was the YAML description. So there's a project called RISC-V config. I've got all the GitHub links on there as well, as you can see. There's a project called RISC-V config, and what it does is it provides a method of describing what the functionality of the device is that you're attempting to implement. And we use that description to configure all of the components within whatever flow you're doing. And in this case, we're talking about verification. So it means that we can configure the simulator, we can configure the compliance test, and we can configure the test generators as well based upon that information. So let's go into compliance testing. So as I mentioned, I'm part of the compliance working group. And we try to come up with a definition of what compliance testing is about. And interestingly, that Krista said something during the members meeting, and he said, well, it's about knowing, have you read and understood the specification? And being able to highlight something which would indicate that you haven't implemented something which is within the specification. Part of the testing that we do, we aim to do things such as we try to use all registers as source and destination in the testing. We attempt to operate on all bits, so where you have immediate values in instructions, attempt to operate on all those bits and expose any issues there. And during the flow, what has to happen is you capture a signature in memory that indicates the results of the test. And this is done effectively by a sequence of instructions that you run, such as loading a register with a value, loading another register with a value, applying those two registers as inputs to the instruction that you're attempting to exploit, and then taking the resultant register and writing it off into memory somewhere. And that builds up your signature. So over the sort of range of instructions that you test, you end up with a footprint in memory that defines the correct behavior, and then you compare that against some known good reference. Now, the good reference can be one of two things, and in fact, when we first started, it's a static representation. So it would simply be a file containing the memory you expected to have been written as part of executing the test. But one of the big problems with doing that is the fact that that test may behave differently depending upon the architecture that you're running on. And so we're sort of moving towards the fact that this, the thing that you reference against should actually be dynamically generated rather than statically generated. Some of the things that we don't try to do as part of our compliance testing, we don't try to stress all the possible functional verification aspects. Look at something very simple. If you had an instruction with 2 input operands and 1 result, then you're looking at a combination of 32,768 possible combinations. That is not what compliance is about. That's what DV is about, okay? We don't try to explore any microarchitectural aspects because we're only exploiting the things that are in the specification, and that doesn't define the microarchitectural aspects. And we also don't try to exploit any illegal instructions. Now, that's quite contentious because we've had lots of discussions saying, well, should you actually prove that a processor that only implements the I extension, that it should not attempt to implement any of the instructions from one of the other extensions? But the decision is made that, no, we don't attempt to do that. One further thing I'd say about doing the compliance testing is that there are some further checks that we do around the actual testing itself. One of these is that we do some functional coverage analysis, and this is quite recent work that we've done. And this was a side effect of something we've been doing with the Google test generator, in that as part of that flow, which I'll come to in a moment, as part of that flow, the sequence generation that goes on ends up producing a coverage report to tell you how well you've exercised the instructions that you attempted to exercise. And we actually use this now as part of the compliance testing as well. And it helps us to guide and report where we need to add extra testing as part of compliance. Now, in addition to that, we also do what we call mutation testing, mutation fault simulation. And the reason why we do this is because coverage only reports to you what has been executed. Now, if you remember, I said that during compliance testing, the measurement is actually made by dumping out the contents of memory and then comparing that to some reference. Well, if you imagine you'd executed a sequence of instructions but never wrote a value into your signature, then it's never observed. So the fact that you executed all those instructions is irrelevant. You've got to ensure that it propagates to something which is measurable, and that's what we do by mutation fault simulation. And the kind of reports you see is something like this. You get a report out telling you that you've exercised these particular instructions with these particular registers, and you've generated negative numbers and positive numbers. And there's a debate going on at the moment as to what data needs to be captured as part of this. We've sort of started with an initial sort of stake in the ground with respect to what we think should be recorded, but we've sort of opened it up to the rest of the compliance group to say, well, is this enough? Should there be more? And if so, what should that be? Now, I'm just going to give you one one quick highlight here, which is coming back to what I talked about with respect to mutation testing. That all of this information is on GitHub, as I said at the beginning. And somebody raised an issue with respect to one of the tests in the compliance suite that executes one of the compressed instructions. And what they said was the test had been written incorrectly in that it attempted to write to an area of memory a result which wasn't part of the signature. So it never propagated out. And this actually shows the importance of doing mutation testing. Now, if you recall what I said at the beginning there, the mutation testing we've done at the moment is only based upon the 32i set, so we haven't done it for any of the other sets, and this is still a to-do for us, so that we can actually validate the fact that even though we've got coverage for these things, you know, that we're actually generating the mutated fault coverage to ensure that we're propagating this. And I was going to quickly show something here, which is the way the mutating fault simulator works. This is how we grade the quality of the test. You can see that it's very fast. You'll see the numbers coming down on the column on the left is indicating the number of tests that have been mutated as the simulator's been executed. And it's going up into the, where are we now, 13,000 tests. And this is just running on a desktop machine here. And the two windows on the right are indicating the amount of parallelism that's going on inside the simulation environment in order to perform those mutated fault simulations. I just thought I'd be interested to quickly show there. As far as the status is concerned with the compliance testing, where are we right now? Well, the base instruction set for integer operations currently contains 48 tests, and that was as of November the 12th in this year. And as far as the coverage is concerned, we've got 100% coverage for the goals that we've aimed to achieve in that test suite. So we're actually very happy with that. Hot off the press is that we have been working on extending the current compliance test suites to include the vector instructions. Now, it's quite interesting that the vector instructions are an order of magnitude more complex than the integer instructions. And as of today, we're up to 2,208 tests, and we're nowhere near done as far as the testing. And this is just compliance. This is not design verification. This is just compliance based upon the parameters I specified earlier that what we're trying to do. We're trying to just test that we've covered the registers, immediate values, things like this. We estimate there's going to be about 10,000 tests by the time we've completed the compliance vector test as part of this process. So that's a bit of a background to compliance testing. I'm going to talk about directed testing. So directed testing is different in that this is where we're trying to get more detailed information about the implementation in a particular device. And they fall into two categories, I think. You know, one that we refer to as test-encoded self-checking and reference comparison checking. So what's the difference there? Test-encoded means that what you've actually done is you've built within the test itself the expected behavior. And so here's some pseudocode to try and show what that means. So you have two integers, A and B, values 4 and 5. You add them together and get a result. And you can assert what that result should be at this point. You say, okay, if I add 4 to 5, I expect the result to be 9. And you can encode that within your application itself. And in fact, one of our partner companies called Valtrix, who are here at the show, if you haven't been to see them, unfortunately, it'll be too late because I think the expo closes after this presentation. But Valtrix have a great product called Sting, and what that does is it uses this kind of technique in that they embed the expected values within the program itself, and so it will self-check and it will report at the end of executing that test. And these are, you know, very pervasive tests that they write. It will report at the end whether or not it produced the expected result during the execution. So what's the alternative? Well, the alternative is to run a reference comparison. So this is where you have your reference device that you've configured using the techniques I described earlier regarding the YAML that defines all of the configuration options for the envelope model. And then you run both of these devices to produce a result which you then compare. And there are two ways of doing this comparison, which are you can either compare them at runtime or they can be compared in some post-processing manner. If you do it at runtime, then you basically have to link these together somehow. If it's done as a post-processing, there has to be some logging or tracing mechanism so that you can do that. So when we do this comparison, how pervasive does your comparison need to be? The very simplest type of comparison you can perform is what we would call a PC comparison at the retirement of the instruction. So what are you actually doing here? You're comparing the program flow during the execution, and then dependent upon the data that's being used during that flow, you expect to see a divergence if one of the models disagrees with the other. And that's either going to be due to the comparison of a value in a branch, it's going to be the value that's used in a jump, or it's going to be an exception that's generated because of the data used in some instruction. With this type of flow, you don't detect data flow differences. You're only going to detect a divergence in the execution. But it's the least invasive for being able to use an RTL description of a design, because you've only got to be able to point at the program counter inside of your RTL code at the point of the retirement of the instruction. So it's actually quite easy to link this together. Now compare this to the second method, which is where not only do you track the PC, but also the write back of your registers and any loads and stores. So here, you're doing the same as before, but additional information. You're comparing your general purpose registers, your floating point registers, your vectors, and your CSRs. One benefit of this is you get an immediate detection of a divergence, because you're also looking at the data, not only the flow of the program as it executes. And in fact, if you were to use these two methods for running compliance tests, the former method of only tracking the PC would likely not detect an issue on the compliance test. And that's because the way the compliance tests are written is it's just a block of linear code. So there is no control flow in there. You don't have unless you're specifically testing a branch or a jump. Typically, if you have a bunch of ads, you're just going to run all those ads linearly, get to the end, and then that's it, job done. So the most effective version is this. Okay, finally, constrained random test generation. So this is what we've been working on recently, and the flow looks like this. We have the Google stream generator. It generates a constrained output for driving into your reference model. You run it through your reference RTL, as you see in this case, and then you have a golden reference to compare it to. You generate some logging information, which in this case is actually disassembly trace, and then you compare it. And in fact, what we've done with this, we've managed to do all of this same flow with the coverage analysis on the bit manipulation and also the vector instructions as well. So I think I mentioned that. So comparison modes. Two modes of comparison, post-processing and DUT encapsulation. So the easiest mode of this is, just to do post-processing of any results. Downside is you could generate very large files, especially for test programs that run for an awfully long time. If you're able to embed your reference into the same environment, then this allows you to have a much more powerful environment because you can find issues at the point of divergence. And in fact, in our case, we've architected our model such that it can either appear as a top-level reference, so it's a simulation environment, or it can be embedded within some other environment. And one of the things we've done is we've recently taken this and embedded it into a system Verilog simulation with DPI to control things like the read and write transactions onto the bus, which means that you can now put this side by side inside of your system Verilog environment and do runtime control compares for both devices. So then finally, high-level logging. High-level logging is a method whereby you're not comparing low-level detail of the instruction execution. You have somehow managed to implement a printf-like capability. And I'm just going to show this slide here, which details the way that we introspect into a design that contains a vector floating point, a vector unit, and we're able to extract information through a mode of discovery and report this at a high level. So here we're not actually looking at the individual instructions, we're getting a high-level view of this. And actually, I'm just going to skip through the last few slides because I've run out of time and say that's about it. There is a tutorial tomorrow morning as well, and we'll be going into a lot more detail of these things. So if anyone's interested, 9 o'clock tomorrow, we have a tutorial talking about all of the technologies I've mentioned here. And so I would recommend you come along to that. Any questions? Yeah.
So how is the performance faster than traditional microcontroller?
So the question is about the performance of the reference model as part of a system Verilog simulation. System Verilog or any RTL simulator is based upon event propagation that causes things to slow down. Our simulator runs incredibly fast, and by that I mean billions of instructions. You know, standalone, it's billions of instructions. So typically what happens when you plug that into another environment, it's the other environment that dominates in terms of performance, and it's really down to the propagation of events that determines how good that performance is.
Do interrupts come into play for compliance testing?
Not right now. At the moment, all of the work we've really done has just been on instruction execution. I mean, not even considering, you know, timers or anything like that. That's a good question. You're right, it has been wrapped in System Verilog DPI. I would defer that question to my CEO over there. It's very new technology that we've worked on. It would definitely be available because we are sharing it with the customer that we've done the work for. So, well, so for our technology, it's an ISS. So we don't model the microarchitectural aspects of the design. However, when we're used as a reference, of course, the comparison that we're making is against the device which would have the effects of its microarchitectural implementation. And this is why I said early on, you know, that the easiest way to do this comparison is the retirement of the instruction from that RTL representation, because dependent upon the complexity of the microarchitecture of that, it can be difficult to extract a lot of this information because it's always distributed along the pipeline. You imagine something with 2 issues as well, you know, or, then it complicates things. And it's always going to be a trade-off as to how much information you can extract from that RTL representation and compare it effectively with the golden reference SAT co-simulating with it.
Question is, when you're running your ISS in a system Verilog encapsulated test bench, is the comparison happening on instruction retirement, or is that post-process?
It's happening at instruction retirement. And in fact, this was something that's very important because what you want to be able to do when you run in this environment is at the point where there's a divergence, and let's assume that you're also capturing the write-backs of the registers and the loads and stores. So you get it at exactly the point where there's a divergence between the reference and the device and the test. What that means is you can look at the entire state of the system and you can determine why something has diverged at that point by, you know, connecting your debugger, looking at the state of all your GPRs, looking at the machine state, and from that you can determine why there's been a divergence in your RTL. I think that's it. Thank you.